Hello, everyone. And let's give it a couple of minutes for everyone to settle down. And I guess, how do you enjoy the conference so far? I'm a bit more enthusiastic, right? I really want to know that I'm going to pay attention because we have a lot of cool stuff to talk. It's the last talk, but we're going to have some interesting demos, I hope. We're going to talk about Cloudnative, streaming and event-driven microservices. And my name is Marius Bogoevici. I'm the project lead for Spring Cloud Stream, one of the projects that we're going to talk today, along with the other one called Spring Cloud Dataflow. I work for Pivotal. I have a deep interest in message-driven architectures. I've been a contributor for Spring integration as well since 2008. So what you'll see really here is basically an evolution of Spring's messaging support and Spring's message-driven applications architecture towards microservice towards the cloud. And the driver, essentially, like if you look at the use cases that we're trying to tackle, are like we're talking about streaming and event-driven applications. And usually what we're referring to is applications where the use cases are things like predictive maintenance, fraud detection, quality of service analysis, IoT, right? Massive quantities of data coming in, massive quantities of data that need to be analyzed in real time, right? So that drives to requirements of high throughput and low latency in the system, right? Whereas the traditional realm of these types of applications was usually batch, we really don't want to make both the business requirements and the capabilities of the different systems have actually pushed the use cases towards a more let's say, more low latency model, where it's not acceptable, for example, to find out that the fraud has taken place a day ago. We want to find out as soon as it happens. The other driver for these types of use cases is not necessarily only the data streaming and analytics. It's, let's say, the more common, the more well-understood domain of enterprise integration applications. It's just that the granularity of the events, the granularity of the data that's coming in and what we see as events has actually increased. So partly because of that, we tend to build more decoupled systems that interact more with each other. So for example, an order processing system would actually consist of multiple parts. An order is coming in, it's processed. Other applications can actually react to that, and then it's a little bit more flexible than if you had everything as a monolithic system in a single application. And as I said, these types of use cases basically drive towards requirements like non-functional requirements like high throughput and low latency, but also functional requirements. Like, for example, grouping of data, ordering, data windowing, right? Usually when you perform, usually analytics is basically performed on data on a specific time window. Or it requires data to be basically, like when we want to detect that the sensor is faulty, for example, we will actually want to see how the sensor has evolved over time. So receiving data, receiving the events, receiving all that information in the proper order actually becomes a requirement, right? And this is driven to other functional changes. So, I mean, you look at the messaging systems that we actually address with these types of applications. We see, besides, let's say, the more traditional JMS and RabbitMQ, right, like very well-established enterprise model, we actually have seen new models such as Kafka or Kinesis or Google PubSub, Azure, like you name it. There's an entire class of messaging systems with the same characteristics, partitioning, strong ordering, and those are basically have been designed to address this specific use case of streaming. Now, In terms of architectural styles, microservices fit very well in that model for a number of reasons. They bring the architectural style advantages of microservices in general, like the bounded context, the ability to develop against a specific domain, but also the development agility, right? If I know that I can focus on a specific problem, I will actually be able to iterate very fast within those boundaries. So that's pretty cool. There's nothing messaging specific in there. In terms of data processing, though, microservices bring something new to the table, bring the ability to actually tune the settings and resource settings of specific processes to the specific type of processing that they do. For example, an application that does data enrichment will require a lot of memory because it caches data, right? So I can actually tune my system requirements towards that. An application that's computing intensive will require more CPU. If I need high throughput, I will have to increase the number of instances anyway, because I will have to face the problem of network saturation, right? Even if I have the fastest computer in the world, I cannot go faster than what basically the network adapter allows me. So organizing your application as distinct parts, as distinct running applications, actually has a lot of benefits for the way you do resource allocation. Messaging itself has its own advantages, especially when it comes to microservices, which are decoupled by default. It adds advantages such as discoverability. I don't need to know who is actually going to receive my message. I just have to send it to a specific destination and trust that the recipient will actually read it from there. Availability. I don't have to, like, if you look at microservices, for example, one challenge in the traditional RPC, HTTP microservices is that I don't know if the service is available or not. In messaging, I have a certain leeway. I just send the message. Usually, it's stored, and when the service is actually available and we'll be able to process it, it will actually be able to handle it, right? Buffering data also ensures that you don't kill the receiving system from with requests. And finally, if you look at patterns such as event sourcing and CQRS, they're actually helping out with ensuring consistency across heterogeneous resources. So one of the problems, for example, is how do you ensure consistency across an entire set of applications, right? You have distributed transactions, which, quite frankly, nobody wants to use it unless they're really, really forced to. And in this case, having applications publishing events when their state changes and have all the other applications in the same let's say in the same topology react to that and update themselves and become eventually consistent is actually a very, very powerful pattern, and messaging enables it. So in that sense, when you consider microservices and we consider their requirements, it becomes really like the modern platforms and what they have to offer become a really, really interesting playground, so to speak, a really interesting deployment target for this type of architectures. And when we talk about cloud native in this sense, we're not necessarily only talking about the fact that the applications themselves are cloud native, but the strategy in which we deploy these applications is specifically targeting these types of platforms, taking advantage of their ability to do resource management, right? You can allocate, like, if you look at what we call basically modern platforms or structured platforms, you have things ranging from, let's say, application platforms, which have, let's say, the entire, like, they have the most sophisticated ways and probably more opinionated ways of managing applications, such as Cloud Foundry. You have like really cluster managers, such as Mesos or Kubernetes, and YARN, right? And what they have in common is their ability to a various degree to ensure, as I said, resource management, scaling, health monitoring, and failover. You just deploy your application, you know it runs, it will be restarted if it breaks, and so on and so forth. You don't have to worry about it. And again, To some degree, some of them support routing and load balancing. You deploy a number of applications, you get a single reference, you get a single address. You don't have to worry about knowing what IP and what port they're talking to. And that becomes very, very important when you look at deploying complex topologies. And that's basically what Dataflow, one of the projects that I'm going to talk today, is actually focusing on. This is the cloud-native aspect, like taking all these things into account and deploying towards them. So the goal essentially here is to be able to do stuff like this, which I'm going to do right now. So what I'm going to start, what I'm going to do is I'm going to start the Spring Cloud Dataflow server. I'm going to run locally. I don't trust the network. It's the worst thing you can do for a demo. And I'm going to start it. And it's basically a Spring Boot application. Let's see. Server. Cool. It's basically just running a jar. And I'm going to start the other component, which is the shell. And these are the two parts of like, the shell is basically one way of interacting with the Spring Cloud Dataflow server. And what I can do here is, can you see in the back? I need to increase the font. OK. So what I can do here is I'm going to start a distributed application that receives data on HTTP and writes it to a file, right? And then what I'm going to do is, this is a stream, right? A stream is essentially a sequence of interconnected applications. I'm going to call it HTTP ingest. And I'm going to say stream create, sorry. I'm going to make it listen to port 1990. And the fact that I'm passing server port here as an argument should tell you something right now, that I'm launching a Spring Boot application that listens to that particular port. And I'm going to send it to a file, and the file writes to a directory, which is temp demo. You see the completion basically kind of giving me hints of what I can do here. And I'm going to deploy this stream, right? And when the stream has actually deployed, I have two running applications. And as you see here, the two applications are the file sync and the HTTP source. And there is another thing there which tells me that it's a variant of this application that actually talks over Kafka. So I have a Kafka broker running in the background. So what I'm going to do next is I'm going to send some data. Right? And if I tail the file where I'm writing, I'm going to call it right. I have some older data from a previous test, which you're going to see what actually this JSON means, but it's going to come a little later. But you see here the value that I just sent being basically appended at the end of the file. So I'm going to send a little bit more just to prove that there's nothing up my sleeve. And I see the data being essentially appended. There's nothing very spectacular in and by itself as a demo. What's interesting about this is that I have two running applications talking over Kafka, both of them being Spring Boot apps. And I basically launched both of them with a single definition, right? So there is much more happening behind the scenes. And actually, I'm going to go and talk a little bit about what happens inside. And the first thing that we're going to take a look at is Spring Cloud Stream. Both Spring Cloud Stream, like for a little bit of history, how many of you have heard or how many of you have used Spring XD? Quite a few. Great. Heard of it? More. That's even better. So Spring Cloud Dataflow and Spring Cloud Stream are two of the projects that have actually come out of a decision that we took a year ago about re-architecting Spring XD. Spring XD was a data platform. Like, we figured out that you can actually build a pretty robust data platform using basically the components that have been part of the Spring portfolio for quite a long time. Spring Integration, right? Spring Batch, they have a pretty long history. Spring Data, right? Actually, it used Spring Boot underneath. And by 2005, we figured out that one thing that we could do better is our approach in how we run the components of the, like how we actually run, how we execute the deployment units of this platform. Initially, we had a container model, and these components would execute inside the container. And then we figured out that basically that wasn't the best thing we can do. And this is where the discussion about the Cloudnative approach comes into play, because we figured out that instead of writing containers actually is not fun. There are so many platforms that do this so much better. Instead of that, we would prefer to write microservices and have a platform that deploys microservices on these structured platforms. And this is basically where the approach came from. Dataflow is the orchestration layer. Stream is basically the API is the framework that helps you write standalone applications that do messaging. A Spring Cloud Task is the framework that allows you to write short-lived microservices. So what you think of as batch jobs, for example, right? So we'll focus on Spring Cloud Dataflow and Spring Cloud Stream. I think a little bit of history helps. It's not incidental that the decision was taken in 2015. It's basically when boot actually has kind of exploded. By then, the cloud platform has actually become very popular. Is the year in which Angel, the first release of Spring Cloud, had actually come out. So a lot of components actually reached a maturity level that we would have been wrong not to take advantage of them. And so we built Spring Cloud Stream. It is, as I said, its core components are Spring Boot, Spring Integration, right? It takes advantage of the ability of, like, really the full stack standalone application model of Spring Boot, like everything that comes there, operationalization, health check, like everything you can get, right, in one Uber jar. With Spring Integration, it takes advantage of messaging, of the enterprise integration pattern implementation of the connectors. It adds its own primitives. So we figured out that there are a few things that you want to see in a message-driven microservice. And we're going to implement them as first-class citizens, right? And the other thing that we decided is that we want you to write message-driven microservices without actually focusing on what kind of middleware are you communicating over, right? We really want to have an abstraction that, while taking advantage of what the target middleware has to offer, isolates the developer of the specifics, right? So basically, you can use the same abstractions whether you work with RabbitMQ or Kafka, for instance. And this is basically the model of a Spring Cloud Stream application. It consists of an application core, which, as I said, is just Messaging, its API is essentially based on Spring messaging. Nothing very specific. It declares, this application basically communicates with the outside world through a number of input and output channels, which are declared on the application. And then the framework takes the responsibility of materializing these channels, inject them into the application, and connecting them to the middleware, to the target middleware. This is basically what we call the binder abstraction, right? In a nutshell, this is the model, like in, let's say, this was the small nutshell, and this is like 10,000 feet nutshell. This is how the structure of a number of interconnected Spring Cloud Stream applications would look like. They're boot applications declaring, like, think of any component, any electronics component model you think. You have the ports, and the ports connect to let's say, these common destinations. And they actually, like, ports can be inbound and outbound. And each application basically just only knows where it has to plug in. It doesn't care whom they talk to, right? And sometimes multiple applications can actually be subscribed to the same destination, so they can work in parallel. And this works even for, like, the approach is that you should be able to interact with non-Spring Cloud Stream applications, not even Spring Boot applications, and quite frankly, not even Java applications. So for example, someone has written, like one of our colleagues has written an application that communicates with Spring Cloud Stream applications, and it's purely in Python, right? Great language for data science. The approach is to be very pluggable. One of the opinionated primitives is durable publish subscribe. So we decided that the fundamental model that we want to focus on is publish subscribe. Why is that? It ensures decoupling between the components. So if I have, for example, I consider a pipeline where you receive data from HTTP, right? You ingest sensor data, you calculate averages, you calculate top-end values, right? This makes it the default pub/sub nature of the interaction makes it very easy to add another component, for example, ingesting to HDFS, or does fault detection. And it actually doesn't work. Like, this works well not only for, let's say, for analytics, right? For like collecting data, like very passive sensor data that's coming in and has to be processed, but actually works very well with, as I say, models such as like more active, more traditional enterprise integration, right? Where a change, like an order comes in, it is taken into account, and then the application actually emits an event that says, okay, an event has been processed, then it can be taken by billing or like processed for shipping and so on and so forth. And then other applications can be very easily added into this pipeline without disturbing the existing structure, and without, for example, the application forwarders having to know anything about it. Of course, that works only well if you don't scale. So there is a competing need that, well, while we like that you can plug in everything everywhere, I really don't want two instances. Like if I want to scale my application and have two instances, I really don't want them to talk over, like to receive the same data, right? So I want them to act as competing consumers. So here we basically borrowed a concept from Kafka of consumer groups, and we actually applied it to other binders, right? Such as Rabbit and Q. So if you declare, for example, a consumer as being part of a group, you get durability. So essentially, the consumer will connect and reconnect and can drop and die and come back and so on and so forth, and it will resume where it left off. And if you have multiple consumers in the same group, they will actually compete with each other, right? They will just receive a sequence of the data. And the other thing that we implemented out of the box was partitioning. So partitioning is a super important concept when you deal with stateful processing. Imagine that you were receiving sensor data, and you want, for example, to calculate averages. Now, the worst thing that you can do is basically round robin over the different, the multiple modules that perform calculations, right? Why? Because you will basically get two values for, like for a given sensor ID, you will get two values computed in each node. None of them which actually reflects the average value of the sensor. You want all the data with common characteristics to be collocated, right? So as part of a first-class citizen in Spring Cloud Stream, we have partitioning. You can specify partitioning expression, and producers will actually ensure that data is sent, like the related data is grouped together, and consumers can actually subscribe to different partitions and receive only the portion of the data that they're interested in, have that degree of control. And then the programming model, which I want to get you and actually start showing you how easy it is to actually use Spring Cloud Stream, is very simple. You create your application, you declare your inputs and outputs through an enable binding annotation, you put a binder on the class path, and that's it, right? And this is exactly what I'm going to show you next. So, one of the nice things about Spring Cloud Stream applications being based on Spring Boot is that I can use things like the Spring Initializer to get started, right? And I can either go to start Spring I/O, right, and generate the application, but I don't want to unzip a file, so I'm going to streamline things and do it directly from Spring's tool suite. And I'm going to create an application called sensor data. Unfortunately, yeah. And basically, I'm going to select the boot version, and I'm going to add the Stream Kafka dependency. I'm going to add the Stream Kafka dependency because I want to build a demo example that uses Kafka. I have other options. For example, I could have chosen Stream Rabbit, and then I could have an application that talks over RabbitMQ. But I like Kafka for this example. And so I'm going to create the app right now. And the starter model, actually, from Spring Boot makes it very easy. It's a very, very simple dependency set. Basically, I have the Spring Cloud Starter Stream Kafka. So now, what I want to do is to start producing some data. So I'm going to add an enable binding annotation, as I said. Oops. Oh, don't do that. OK. That completes now. And enable binding takes as an argument one or more interfaces, which declare channels. And interfaces, I actually have a set of three predefined interfaces that correspond mostly to the mostly used models, like one input channel, one output channel, and one input and output channel. They're called source, sink, and process. But you can create your own. You can create actually as many channels as you want, right? So I'm just going to go with the one that's out of the box. Here's how it looks like, right? And what I will want to do is to, I'm going to send some data, right? And here is, so I'm going to create an inbound channel adapters. Which how many of you are familiar with Spring integration or using it? You should. I think it's a great framework. Source dot right? And I'm going to bind the channel, and I'm going to create, return a string, and I'm going to call it send data, and I'm going to create a bit of random data. Okay, and I'm going to say string. Okay. And call it, I'm simulating an integer between 0 and 9, and that's concatenated with, so it's more like a sensor ID plus the value between 1 and 100, right? And I probably missed something here. Yep. Right. So what I'm going to do next is I'm just going to start this application. Oh, what I need to do next, quite important, is, I mean, if I don't do anything, it's going to write to a Kafka topic named output, but stream bindings. So I can add a property that says that the destination for the output channel should be a topic called sensor data. And I'm just going to create that, and I'm going to start the application. And what I'm expecting to see right now in Kafka, you see a topic being created. So that's one of the features that can be enabled or disabled, but like you do it by default, stream creates the topic and starts sending data. So now I have to receive it, right? And I'm going to do it pretty much the same way. And I'm going to log it. And I'm going to use stream Kafka as well. And the only thing I have to do on the other end, on the receiving end, is to connect to, so I'm sing.class, not sing.input. I'm going to create a different binding with an interface called sync, and sync, right, has only an input channel, right, so it receives data. And the next thing to do is I'm just going to create a method that can actually process this data. Right, and I'm going to say it's a void, it doesn't send anything, and it's just log data and receives a string. And everything is actually passed as a Spring integration message, but I'm going to go to the payload directly and I'll say system out. And it's a demo, so I can use system out print line. Don't do that in production. And that's pretty much it. The only thing I need to do is obviously kind of make these two applications to agree with each other, right? And I'm going to say Spring Cloud stream bindings input destination. It's sensor data. And I'm going to do something else here, and I'm going to assign it a group. I'm going to make it part of the group so it receives data from the beginning of time, and also it can stop and resume. So group is logger, something. And I can start this application as well. Oh, and because both of them are Spring Boot application, it could be a good idea to set the port to an arbitrary number. I'm not using the actuator endpoints. So I'm going to start this application, and it's going to crash. And let's see. What did I do wrong? Of course, I didn't tell the listener what channel it should listen to, right? So validation actually didn't let me start. And as I hope most of you are able to see, you see basically data flowing into the other application. So essentially what I did so far is I created two applications that talk to each other over Kafka, over a common destination, path information, so on and so forth, right? So this is quite simple. What I'd like to do is I'd like to take this a little bit further and say, well, if I really like the notion of like me manually marshalling and unmarshalling data, but wouldn't it be better if the framework did that for me, right? So I can create a class, a POJO called sensor data. And right, and I'm going to create this. I'm going to generate getters and setters for these methods, and I'm going to generate also constructors. Okay, and I'm going to generate another constructor just for, actually I don't think I need it, so that's fine. It's not unmarshaled. Actually, it's a better idea not to have it. And, oh, I think I need it in the other project. I'm just going to move it over. Okay. So I have this class here, and instead of sending out strings, I'm going to send sensor data. And I'm going to, instead of returning the string, I'm going to say new sensor data. And I'm going to pass it like this. And normally what's going to happen when I send POJOs like that is that the framework serializes them. So I don't really want to do serialization because obviously I will have to have the same class on the other side. So I really want to use a more portable format. In this case, I'm going to use JSON. So I'm going to tell it, I'm going to tell Spring Cloud Stream that the content type is application JSON. So this application runs, and if I start the log, I should see the JSON strings basically flowing into the application. So it's kind of cool, but then again, I don't want to parse this JSON manually. So what I'm going to do, I'm going to stop this. And I don't want to share the class, right? So I'm going to create a new class on the other end. And I'm going to call it received sensor data. And I'm going to let the framework basically do the unmarshalling for me. So okay, generate getters and setters. All right. And what I'm going to do next is also I'm going to generate a toString method, right? And so the log, I'm going to tell it to use receive sensor data. And there is a concept, like there is like Spring Cloud Stream essentially passes and will adapt the different binary implementations to pass some sensor headers, some content headers into the messages that are basically exchanged, so that the receiving end can actually infer something and do some transformations. So what I'm going to do next is I'm going to start the application. I'm going to start the log again. And as you see, what's flowing into the system right now, like what's logging, is really the POJOs. So basically, the conversion was automatic. The method itself can actually, you can basically write your code in like using POJOs and domain objects, and the framework will actually take care of the conversion and the coercion of the data for you, right? And that's a very powerful thing, especially when you're trying to make, I mean, one of the things that we've been trying to make is, as a goal, is to make developing, let's say, message-driven applications as easy as it is to write, let's say, web applications, for which that kind of thing is kind of understood, right? So we want to apply the same logic, the same patterns, the same thinking in this type of scenario. And you've seen Spring Cloud Dataflow at work, right? You've seen basically what the demo at the start and how it runs, basically. How can I start this pipeline? Essentially, what it consists of is essentially an orchestration layer that has a DSL for defining stream topologies. It has a RESTful API that you can actually target to deployment and interact with the server. It has the shell that you've already seen. It has a UI that you will see in a minute. And it also has what we call a portable deployment SPI, right? And a part of that, there is an entire ecosystem of Spring Cloud Stream applications written exactly for being orchestrated with Spring Cloud Dataflow. And they cover basically the majority of the breadth of integrations that basically Spring integration has to offer. So you can find there anything, like applications that write to Cassandra, applications that stream data from JDBC, applications that stream data from S3. Like, really, just go to on GitHub, and it's Spring Cloud Stream App Starters, and you will actually find a ton of stuff, right? And the nice thing is that they can execute standalone because they're Spring Cloud Stream applications, but they actually work even more interesting when they're orchestrated with Spring Cloud Dataflow. And the second part underneath Dataflow is essentially, like the orchestration part is the ability of declaring your topologies, your streams, as sequences of pipes and filters. So when I wrote that HTTP pipe file thing in the beginning, I was really telling, go find the application that you know that's HTTP, that you have registered, find the artifact, then connect it to the file application. And when I say connected to, you've seen how I had to, for example, specify common destinations in both applications that I have created, right? Because they are Spring Boot applications, Spring Cloud Dataflow can pass actually environment variables or start parameters that they actually customize the common destination. When you launch them, you don't have to know what the name is. It's just going to be done for you automatically. And there are other parameters that are configured. Like, I don't know, instance count, memory, basically anything that partitioning, for example, is another thing. It's actually pretty powerful. In terms of deployment, Spring Cloud Dataflow basically uses another project called Spring Cloud Deployer that provides an SPI for running applications to any modern runtime. So basically what it does is it defines the SPI, has implementations for, we've seen the local implementation actually at run. There's, as I said, Cloud Foundry, YARN, Kubernetes, Mesos, and Marathon. And the interesting about it is that it supports different types of resources. So you can package your applications as Spring Boot Uber jars and deploy them. You can package your applications as Docker images and deploy them. Of course, on a runtime that actually supports running Docker images, right? You can place these things in different locations. So you can have, for example, Uber jars sitting in an HDFS if you want to deploy in YARN. Or you can have Uber jars sitting in your Maven Enterprise repository if you want to deploy. Things like that. Or you can have applications sitting just on a static file server. Right. We're 5 minutes, so probably just wrap it up with a quick final demo. The only thing that I want to get to you is I want you to take this image, even if it cuts into my demo time, and look at this. Like, this is basically the deployment model with Spring Cloud Dataflow. Spring Boot applications running independently, interconnected, the links between them being created from the DSL by the deployment SPI, using using a pluggable SPI, an implementation according to the target environment. But it doesn't matter whether it's Cloud Foundry, YARN, Mesos, Kubernetes, local, or whatever. That is an abstraction that is kind of, you don't have to worry about, right? That's something that Spring is very, very good at. And just a final thing, right? I just want to show you how easy it is to actually add and create and deploy an application using Spring Cloud Dataflow. So starting with the demo, right, that I just did, right, that one that basically was piping data to a file. Instead of doing that, I will want to use the sensor data generator and actually have it pipe to the file. So let's see if I can do it in a very short time. First, I'm going to destroy the streams. Bong. OK. It works, but the error message wasn't very friendly. Basically, I'm going to destroy all the running applications. And I'm going to say, first, I'm going to go to my demo. So sensor log. I'm going to install in Maven. OK. And after I install it in Maven, I'm going to say module register. And I'm going to give it a name, and I'm going to call it sensor. Oh, sorry. I want to send the sensor data. Sensor data. I'm going to call it, the type is a source, and the URI is Maven. And because this is deployed locally, it knows where to deploy. It's Spring IO 6 called sensor data, and it's 001 snapshot. OK, so I registered the module. I'm going to see if it's registered correctly. I'm going to get some information about it. So I'm going to call it module info source sensor data. OK, probably not. Yes. It's Spring IO 16, not Spring IO 6. OK, and the next thing I'm going to do, I'm going to create a stream, create sensor. OK, and I'm going to call it definition is sensor data piping to log, not piping to file, directory equals temp demo, and I'm going to deploy it. OK. And you see the application running and basically piping the JSON directly into the file, right? With 20 seconds over the time. Okay. So thank you very much. And if you have any questions, or please have my Twitter address, and feel free to ask. Not sure how much can you stay, but I'm here to answer your questions. So that's a very good question. So if you're talking about monitoring, what aspect of monitoring are you talking to? You can do different things. On one hand, you can. So the question was, how can you monitor events? Either, remember that this is pub sub, so you can actually listen to see what's being sent on the topic. If you want to monitor the performance, for example, there is integration with Zipkin, the tracing framework, which will actually tell you not necessarily what's in the message, but how they flow. What's their latency? How far, how do they travel across the system, right? And we actually have other ideas of how we can improve that process. So, but that's pretty much it. Also, being Spring Boot application, all the applications actually have their own health checkpoints and expose metrics that come from Spring integrations. There is a very rich ecosystem that. Any more questions? I will still be around here, so feel free to come and ask. If not, have a great weekend and have fun and safe travels back when you travel.